Okay, so this is the RBC model setup. Like I said, it's basically just a neoclassical growth model, but with shocks to technology, which are also government purchases, but we're mostly going to focus on the case where the shocks are coming to technology. In addition, this model is going to have a utility function that includes leisure. Okay, so far we've assumed that the labor supply is fixed. Basically, people work a certain amount regardless of what the wages are. We're going to change that here, and there's a reason for it. The reason, of course, why I would have asked you in class, but the reason is that we want to focus on employment issues during a recession. We want to see if our model can match how people are employed or unemployed during a recession. And to do that, we need people to choose how much they work. Otherwise, we just have a fixed labor supply. So it's important for us to put leisure into the utility function. This is kind of the way that with these economic models they work, is you want to make the models as simple as possible, but still containing the features that make it possible for us to analyze what the questions we want to answer. Right, it's also going to be discrete time. This doesn't matter. Sometimes, time is discrete, time is continuous. It's a modeling decision. It's just a tractability thing. There's nothing deeply intuitive about why we want that. Okay, so we're going to have time is discrete, right? So 0, 1, 2, up to infinity. We're going to have a large number of firms that are going to take prices as given. So in particular, firms are going to take wages and the cost of capital, the rental rate on capital is given. Firms, again, are going to be sort of static. So their problem is just going to be maximizing profit this period. Whereas, since there's a large number, there's going to be a free entry. They're not going to make any profits in equilibrium, so they're not the super interesting part of the economy. The interesting part is the households. So these households can hold capital, so that means that they can save, right? They can invest, and just like before, as in our growth model, we have to think about if population is increasing, we have to think about how households, or how the economy are, how as planners we should think about future generations. So we can do that by using this concept of households where, they kind of discount future generations. They care a certain amount about their children, about a little bit less about their grandchildren, a little bit less than that about their grandchildren's grandchildren, etc. Whether that's reasonable or not, that's what we're going to do. And we're going to have 3 inputs into production, just as we've had in all of our models, I think, so far. Well, except for the endogenous growth model, right? Because there we had intermediate goods going into final, and then labor going into intermediate, and no capital. But, in the other 3 models, Solo, neoclassical growth model, and OLG, there we had 3 factors: capital, labor, technology. Production function is going to be Cobb-Douglas, same functional form we've been using pretty much for this entire course, except for endogenous growth model. All right. So just rewriting that slide, we're going to think about the evolution of capital. Okay, so how do we get new capital? How do we maintain our old capital? It looks like this, and you look at this equation, you say, wait a second, this is a little bit different than what we've been looking at. Previously we had this thing about K dot is equal to, we had remember something like SY in the Solo model minus delta K, right? How do we square this with that? It looks a little different. Well, actually it's the same. So here you see we have a KT plus 1. Here we have a KT. So kind of a natural way to think about this would be KT plus 1 minus KT is equal to investment minus depreciation times K. Now this looks very similar to this equation up here. And these are kind of analogs, right? K dot is the change in the capital stock, and KT plus 1 minus KT is also the change in the capital stock. All right, so these are really the same equation, just one's the continuous time analog, one's the discrete time analog. All right, so here you can see we've got a KT, and then we're going to change this investment to this equation, which is just another way of writing investment. So it's going to be output minus consumption, and then also minus government purchases. Again, we're mostly not really going to focus on that. I think it's a little bit weird the way that it's put into these models, since the government purchases don't do anything. So all they do is they just take away output. So I mean, there can be nothing but badness coming out of these government purchases in this way of formulating them. So I don't really love the discussion of them. But, you know, it's theirs in the textbook. So investment is going to be output minus consumption minus the amount that the government consumes, if you like. So, you know, you can rewrite this equation this way, right? Furthermore, we're going to be able to write the real wages, and I believe if I scroll on here, the real rate of return on investments. So wages, they're going to be the same as what we had before. Just again, you know, slightly different because it's a continuous time version, but otherwise very similar. So you know, it's just going to be the marginal product of labor, right? So the derivative of the production function with respect to L. And you can see here that if you write little k, in this case it would be 1 minus alpha little k to the power alpha at. Okay, so this is good. This is wages per worker. If we had wages per unit of human capital, then it would be WT divided by A, which is, and then that looks very similar to what we had previously. Very similar. I'm just hesitating a little bit because if you remember last time, what we had was that WT is equal to, let's see, this is the continuous time version now. Get myself in trouble, let's see how well good my memory is. It was equal to F little k minus little k times F prime of little k. Okay, so in this version with Cobb-Douglas production, this would be k to the power alpha minus k times k to the power alpha. Oops, little mistake there. K times alpha times k to the power alpha minus 1. Oh my gosh, look at this. 1 minus alpha k to the power alpha, and it ends up being exactly what we had over here, because this wage that we were looking at was wage per unit of human capital. This wage we're looking at here is wage per worker. Okay, so these are actually identical expressions. Very cool. So that actually doesn't depend on whether it's continuous time or not. That's actually just the same expression. The reason it looks different is because here we have the general version, and here we have the version for Cobb-Douglas production function. All right, this one though is a little bit different. So, you know, I've been kind of trying my best to keep these terms straight, but now you're gonna see where it actually matters. So I've been talking about the rental rate of capital and the rate of return on capital. Okay, so you know, those, I've been kind of using them almost interchangeably, but they're slightly different. The rate of return is what I expect to get back on my investment, whereas the rental rate is what firms are paying to use capital for a period. So what are firms going to pay? They're going to pay the marginal product of capital, but how much do I get back? Well, I get back the marginal product minus the amount that the capital is depreciated, right? So here, because of depreciation, we're actually driving a wedge in between the rental rate of capital and then the rate of return. Okay, so if you remember, when we actually analyzed a model that had where we calculated this, which was the neoclassical growth model, we had assumed that there was no depreciation. That's why those two things were identical. Once we had depreciation, then there's this little wedge in here. Okay, so you can do the calculation, and sure enough, it's going to look very similar to what we had before. This is just the derivative of the production function in terms of little k, right? So, you know, f of little k, if it's Cobb-Douglas, is equal to little k to the power alpha. So f prime of k, or the marginal product of capital, is equal to alpha times k alpha minus 1. That's what we have here. You can see that we have the AT and the LT on top, so that's why it's 1 minus alpha, right? If we have 1 over little k, then it would be 1 minus alpha minus delta, because that sticks around. So this is the rate of return.